All right, let's dive in. We're going to explore two totally different but equally powerful ways of thinking about how to build stuff that, well, simply cannot fail. We're talking about a world of super intense rules, incredibly high stakes, and some truly brilliant engineering. And it's all governed by these big, complex standards that are now, interestingly enough, starting to overlap. I mean, it's really the ultimate engineering question, right? How do you build something that absolutely positively cannot fail? We're not talking about something that's just unlikely to break. No, we're talking about situations where failure is so catastrophic. It's not an option. It can't even be on the table. So where do you see this kind of high stakes design? Yep, exactly. We're talking about places where you get 0 second chances. Think about it. A satellite orbiting the Earth. You can't just send a mechanic up there. Or the cockpit of a fighter jet. A pilot's life literally depends on every single component working flawlessly under insane G-forces. And of course, a life support system. I mean, the name says it all, doesn't it? This is the world we're about to step into. Okay, so here's how we're going to break this down. First, we'll look at the two different worlds of standards. Then we'll dive into how they create their blueprints, how they design for safety, and the insane tests they use. And finally, we'll see where these two worlds are starting to collide. All right, first up, the two worlds of standards. And this really gets down to a battle of ideas, prescription versus principle. So this slide just nails the difference. On one hand, you've got the military way, or MIL standard. The best way to think about this is like a super detailed recipe from a master chef. It's been perfected over decades. It tells you exactly what to do, step by step, to get a perfect result every single time. Then you have the global way, the IEC. This is less like a recipe and more like a masterclass in food chemistry. It doesn't tell you how to bake the cake. It teaches you the science so you can prove why your cake is safe to eat no matter what recipe you come up with. So let's zoom in on the military's playbook for a second, specifically MILSTAND 100G. This thing is, well, it's obsessed with control and traceability. And I mean obsessed. Every single component from every supplier gets a unique part number and a cage code. Want to change one tiny thing? Not so fast. That change has to go through a whole formal process. It's evaluated, documented, tracked, the whole shebang. The goal here is absolute, total knowledge of the history and pedigree of every single part in that system. Okay, now let's flip over to the global approach. The core idea here is something called hazard-based safety engineering, or HBSE, and it's a totally different mindset. Instead of a rulebook telling you how to build something, it makes you ask a much more fundamental question. What could possibly go wrong? You're basically looking at your product as just a bundle of energy sources, electrical, thermal, whatever. And your job is to figure out all the ways that energy could escape and hurt somebody. So what does that actually look like in practice? Well, it's a pretty logical 4-step process. First, you identify all the energy sources in your gadget. Second, you classify them. How dangerous are they? Is it a class 1, something you'd barely feel, a class 2, which would be painful but not cause an injury, or a class 3, something that's definitely going to cause harm? Step 3, you put in safeguards, things like insulation or safety locks, to keep that energy contained. And then the final and most crucial step, you have to test the heck out of it to prove your safeguards actually work. It's all about proving it's safe, right from the ground up. Okay, so let's get into our first big comparison. How do these two worlds actually document a product? What does the blueprint look like? And wow, the difference here is just night and day. Milstead is super strict. It tells you the exact format your drawings have to be in. It's all about that unique cage code and part number for total top-down control. But IEC, honestly, it couldn't care less what your drawings look like. As long as your paperwork proves your safety case, that you've thought about the hazards, and your warning labels are clear, you're good to go. And that leads us right into the next big question. If the paperwork is so different, you can bet the whole approach to safety design is, too. So how do they prove a product is actually safe? We're seeing that same pattern again, right? The military way is to zero in on specific critical safety items, or CSIs. These are the components where if they fail, it's game over, catastrophic. And if you touch one of those CSIs, bam, massive formal review. The IEC approach, though, is much broader. It's not just about a handful of critical parts. It's about doing a risk assessment for every single potential hazard. So if you change anything that might affect a safeguard, even a simple piece of plastic insulation, you have to go back and prove it's still safe. Okay, so your design is safe on paper. But how do you prove it can actually survive in the real world? Or, in a world that's way, way harsher than the real one? Well, that's when you have to run the gauntlet. And get this. This is just one of many, many brutal tests from the military standards. And it is every bit as violent as it sounds. First, you bake a part at 257 degrees Fahrenheit. Then, in less than 10 seconds, you dunk it into a freezing cold bath at minus 85 Fahrenheit. That's an insane temperature swing, almost instantly. And you don't just do it once. You do it over and over and over again. The whole point is to force any tiny weakness, any flaw in the material, to show itself. So, how on earth do you design something to survive that? The answer is a really key engineering concept called derating. And this car analogy is perfect. You'd never drive your car with the engine constantly screaming at the red line, right? You know it's just a matter of time before it blows. Derating is exactly that, but for electronics. You take a part that's rated, say, for 100 volts, and you deliberately only run it at 50. You're building in this huge safety margin so it's never even breaking a sweat. And this table shows you exactly how that works in the real world. This is a real guide for capacitors from a military standard. See, for ceramic or tantalum types, the rule is simple. Use them at half their rated voltage. But look at what's even more interesting. The parts that are just flat out not allowed. For these super high reliability jobs, certain components like aluminum electrolytic capacitors are just forbidden, banned. It doesn't matter how much you derate them, they're considered too much of a risk. So you've got these two very different philosophies, right? The super strict, by-the-book military way and the flexible, principle-based global way. And for a long time, they kind of stayed in their own lanes. But that's changing. Today, in our world of super complex, interconnected tech, these two worlds are starting to collide. And here's the real punchline. The best way to do things today is to actually take the best from both worlds. You need that obsessive mil standard traceability to know exactly what's in your product and control your supply chain. But you also need the IEC's big picture risk assessment to think through every possible way things can go wrong. You need the military's insane environmental tests to prove it's tough, and you need the IEC's safeguard tests to prove it's safe. This is really the key idea to take away from all this. It's not an either-or thing anymore. If you want to build something truly reliable in the modern world, you need both. You need the military's prescription to prove what you built, the exact history of every part, and you need the IEC's principles to prove why it's safe, the deep fundamental thinking behind your design. So let's bring it back to that baking analogy one last time, because it works so well. At the end of the day, both philosophies want the same thing. A reliable result. The mill stand approach gives you that perfect, proven recipe. You follow it to the letter, you get a perfect cake every time. The IEC approach teaches you the chemistry of baking. It makes sure you understand the science so well that no matter what recipe you use, your cake will never, ever catch on fire. And that really leaves us with a final big question. As our technology gets more and more complex, more interconnected, which of these two philosophies is going to define the future of reliability? Are we going to need more and more detailed rulebooks to keep everything under control, or will we have to lean more on a deep understanding of core principles to keep things safe? Honestly, that's a question that engineers are going to be wrestling with for a long, long time.